Okay, so group B, we'll talk about frequency mixing. A mixer is a circuit that outputs the sum and difference of two input frequencies. And that process is also called heterodyning, where we're going to basically generate a new frequency by mixing two other frequencies. Now, in a normal mixer, you get the sum and difference of the two. So in this case, we're doing a down conversion. So we're feeding in an RF signal and a local oscillator signal into this mixer, and we're getting out an intermediate frequency. So here's our RF input. Here's where our local oscillator or VFO is. And the difference between those is going to be our intermediate frequency. And that's showing up down here at this point. So let's say that was 455 kilohertz. That would be the difference between the local oscillator and the input RF signal. So you're going to tune your local oscillator 455 kilohertz above this frequency. If you were doing an up conversion, which would be like for transmitting, okay, I'm feeding an intermediate frequency into the mixer with a local oscillator, and I'm going to get an RF frequency out that's the sum and difference of those two inputs. So here's our intermediate frequency. Again, let's say it's 455 kilohertz. Our local oscillator is up here at, say, it's 7 megahertz. So I'm going to get these two side bands, basically, offset by 455 kilohertz above and below that local oscillator frequency or my VFO frequency. And then if I was doing single sideband, I'd get rid of one of those before I actually transmit. That's how the amateur tune, but the military actually tunes the local oscillator instead of sideband. Yeah, but on single sideband, there is no, I mean, you have to guess at the local oscillator frequency because it's not there. On the receiver, it's not there. That's why when you tune an SSB signal, uh, it's you get a Donald Duck and you're in a sound like you're in a barrel because the you're converting it to an audio frequency that's not the right offset from where the carrier should be. So you get all kinds of frequency shifts and it really sounds weird. What is another term for the mixing of two RF signals? What combination of a mixer's local oscillator and RF input frequencies is found in the output? Okay, let's see. In a superhead, the signal from the antenna combined with a signal from a circuit called the local oscillator or VFO produces your intermediate frequency so that you can do filtering and stuff on at much lower frequency. It's a lot easier to do in analog circuitry. So when you tune the radio, you're actually varying the frequency of your local oscillator or VFO, which is what it's normally called on the radio. In this example, we have our local oscillator set to 1455 kilohertz, and we've got 5 RF stations out here. And the green one is centered at 1,000 kilohertz, and we got two slightly above it, adjacent, and two below. So when we mix these signals together with our local oscillator, okay, we're going to get a IF frequency of 455 kilohertz in our passband, but we're also going to see these other ones adjacent to it. So as long as the passband is fairly narrow and has good skirts on it, we're going to reject the red, yellow, blue, and purple signals. But the only thing we're going to see is this green one, which is within the passband. So that's one of the reasons why you want to control how wide your passband is when you're trying to receive a signal. If I had it very wide, then I'm going to get all these other signals in there at the same time. It's narrow, I wouldn't say clipping per se, but definitely you're going to change the audio quality. Which mixer input is varied or tuned to convert signals or different frequencies to an intermediate frequency or IF frequency? The old local oscillator. Okay, when a signal is tuned in, you can have another signal interfere called image response. So, example here is you've got your VFO set for 13.8 megahertz, and you're receiving a 14.255 megahertz signal, the one you want to listen to. So the difference in frequency is 455 kilohertz, which is what your intermediate frequency is in the receiver. Now, it turns out you could have a signal coming in at 13.345 megahertz, which is 455 kilohertz the other direction. Okay. So the mixer is going to put both of those signals at the same point. So I'm going to receive both of those. And that's called an image response. So I have to, on the input, be able to have enough selectivity, let's say, to reject this lower frequency signal when I'm trying to get the 14.255 signal. So I have to have a passband that's going from my 13.8 to 14.255 to get rid of that image down there. And this is just showing all of the different products that occur out of that mixer situation. So you can have a multiple of 2 of the IF frequency or multiple of 3 of the IF frequency. There'll be lower amplitudes, but they'll still be there. So normally they would be outside the passband, so you wouldn't worry about it. And I guess the key thing is with the image response, the way they're going to word it in the question is if it's twice the IF frequency, which is in this case 455 and 455. So it's coming in at twice the IF frequency difference from the one you want. And then you would see it as an image in your IF. So what is the term for interference from a signal at twice the IF frequency from the desired signal? Image response. The question sounds a little confusing. Okay, Okay. We have another thing called intermodulation, where if you have nonlinear devices, and actually they don't even have to be in a radio, it could be a rusty joint on something that can act like the old-fashioned sort of crystal detector things, and be picking up a signal and re-radiating it uh, with this intermodulation products. So you wind up with a lot of spurious outputs, the nonlinearity, and that's one of the things when they design receivers is trying to keep all the circuitry as linear as possible because in the analog world, you're going to have a little bit of nonlinearity, which is going to give you some spurious outputs. That was one of the things on the Bofang handy-talkies, at least the first generation that came out, had all kinds of spurs side of the normal thing. Most of the clones claim to have fixed that. I don't know if the newer Baofeng models still do that or not. So the product of F uh, twice F1 minus F2, twice F2 minus F1, some difference of those, are going to be what we call first order or odd order intermodulation products. So these higher ones, which would be 3 times, 4 times, or second, third order, even, and odd as you go up. So what process combines two signals, a nonlinear circuit or connection, could even be a feed line connector that's loose, to produce unwanted spurious outputs? Intermodulation. Which intermodulation products are closest to the original signal frequencies? Odd order. First one. Which of the following is an odd order intermodulation product of frequencies F1 and F2? Harlan, because the difference between F1 and 2 is a single one where this is 3 times, this is 5 times, so it's going to be a second order. Multipliers. In an FM transmitter, you can generate a signal at IF frequencies and then multiply the frequency to a higher value to actually transmit it. So if you're transmitting at 144 megahertz, you may be generating a signal at a much lower frequency and you multiply it 2, 4, some number of times to get it back up to your output frequency that you want. And that's done by having an amplifier similar to, there probably are, Class C amplifiers, where the tuned circuit in the amplifier is tuned for a harmonic of the input signal. So if it's tuned to the first harmonic, uh, you're going to get a frequency that's twice what you put into it and amplified. So you may have in this picture, there's 2 doublers. So the output frequency is going to be 4 times what we're dealing with over here. In some cases, there's a tripler where you can have it on the third harmonic and actually multiply it by 3. I don't think I've seen any more than 3. but you can combine them like they did here with two doublers to get 4. Or if you had two triplers, you could get 3 times 3 or 9. So you can get a lot of uh, multiplication factors depending on how you arrange them. And that's just so that you can operate on things with filters and stuff at a much lower frequency. So what is the stage in a VHF, UHF, FM transmitter that generates a harmonic of a lower frequency signal to reach the desired operating frequency? Deviation. So when we generate FM, we're going to change the frequency of the carrier or deviate it. And in this case, we're going to represent that as a delta F, or the deviation, which is the peak deviation of the signal. Now, we also have the modulating signal, which is an AM signal, and it also has a peak deviation in frequency. So in order to figure out how much deviation you need, in normal amateur radio FM, the deviation is 5 kilohertz. So at 144 megahertz and with a 5 kilohertz deviation, if you're generating the signal at a much lower frequency in the transmitter, you have to look at the ratio of the deviation at the output frequency versus the frequency at your modulating frequency. So if your output frequency was, say, 12 times what you're modulating at, then the modulation deviation is going to be 1/12 of what you need at the output in order to get to 5 kilohertz. So you divide the 5 kilohertz by 12, and that's how much you would deviate your lower frequency signal to maintain 5 kilohertz deviation on the output. Am I making sense? I'm glad I already got my ears. This is not Dexter. So in this example, for a 5 kilohertz deviation at 146.52 megahertz, okay, and we're using a modulating frequency of 12 megahertz, then we've got the ratio of the modulating frequency divided by the carrier frequency, in this case, the 12 over the 146, times our 5 kilohertz, was deviation that we want on the output. So we do that ratio, and it says we need to deviate 416.7 hertz of the modulating frequency, the local oscillator that we're modulating. And the FM modulation frequency is the highest modulation frequency. So it would be whatever the highest pitch of your voice would be. Does that mean we have to change it for women versus men? You want to get up at least 4 or 5. But then normally I think we kind of cut it off at 3 kilohertz. So, but whatever. Okay. There's a thing called Carson's bandwidth rule, which is how you determine what the bandwidth would be for a FM modulated signal. And you take the peak deviation. So for our amateur FM, it would be normal wideband FM, or normal FM, it would be 5 kilohertz. We add that to the peak modulation frequency, which in this case we're going to say is 3 kilohertz, because most of the voice information is 3 kilohertz and below. That's why analog telephones cut off everything above 3 kilohertz. We add them together and multiply it by 2, and that gives us the bandwidth. So for a typical FM signal with 5 kilohertz deviation and 3 kilohertz modulating frequency, the bandwidth is 16 kilohertz. And we normally separate those channels by about 25. So what is the frequency deviation of a 12.21 megahertz reactance modulated oscillator in a 5 kilohertz deviation, 146.52 megahertz FM phone transmitter? You remember the number. Didn't have to use your calculator. Remember how to do it with the calculator, because you'll forget the number on the test. But it's simple. You just do the ratio and multiply it times the deviation that you want at the end. So what is the total bandwidth of an FM phone transmission having a 5 kilohertz deviation and a 3 kilohertz modulating frequency? So we use Carson's rule, and 5 plus 3 is 8 times 2, 16. Duty cycle. It's the ratio of the time on versus the total time. So per unit of time, what percentage of time you're actually transmitting. So it's the ratio of T on to T total. When you get very high duty cycles, you could actually exceed your transmitter's power specifications, and they will normally list it by different modes, where you have different transmit power for different frequencies and for different modes. In the case of the digital modes like FT8, it's about a 50% duty cycle. In some cases, you actually have to cut back on your power. Operate. I have that problem with my vertical antenna, because even though it's rated for more than 100 watts, if I transmit FT8 at 100 watts, it heats up the loading coil, the ferrite in it, and the SWR just keeps, the hotter it gets, the more it increases. And at some point, I could either ruin the toroid in there or have it explode. No, it wouldn't, because I'd have to replace the antenna. You have a camera on there antenna? Huh? You have a camera on there. It likes to watch the explosion. So why is it important to know the duty cycle of the mode you're using when transmitting? You kind of need to know the symbol rate of the mode you're using. And this really applies to digital modes where what you're sending, as we call symbols, because it may represent more than one state of information. If you're doing FT8, you need 50 hertz. If you're doing PACTOR or PACTOR 3, which is a much older digital, it's actually a packet mode, it requires 25 or 2300 hertz. And if you're doing FM phone, FM voice, with the 5 kilohertz deviation and 3 kilohertz modulating frequency, you need 16 kilohertz. So what is the relationship between transmitted symbol rate and bandwidth? Symbol range less. The one in the previous chart, PACTOR, was very wide bandwidth, but it has a very high symbol rate, which is why. Signal to noise ratios. Okay. Noise is a real problem when you're operating digital modes. If you get too many errors in a digital mode, you basically can drop the connection or you hear nothing on like a digital voice mode. It's either crystal clear or it's not there at all. So that's one of the reasons why you need to match the receiver bandwidth, or if you're changing the bandwidth in your IF amplifiers, and you want that as close to the bandwidth of the signal you're trying to receive as possible. And the reason is, if you look at the signal to noise ratio formula, it's the ratio of the power of the signal divided by the power of the noise. So you've got a noise floor down there. So the wider your bandpass filter is, the more noise you're bringing in. And it's the area under the curve of the power of that compared to this little narrow band signal in the middle. So the closer you can get that pass band to the bandwidth of the signal, the less noise power you have in the equation. So you get the highest signal to noise ratio. So why is it good to match receiver bandwidth to the bandwidth of the operating mode? Okay.